In this video, we are going to talk about simulation, and what is very important, we are going to use a free tool, and basically everyone can then simulate even PCB traces, correct? That's what we are going to talk about, Eric.
Yeah, that's basically it. It's a very brief introduction to a free open source simulation tool that you can use. It's a SPICE simulator. And so anything you can do in SPICE, you can do with this tool. And it's especially valuable for signal integrity because it also understands S parameters. And you can simulate and view S parameters as well. But we're not going to talk about that one today.
As parameters, it means, for example, from existing PCB, we can generate a model, as
Yep,
parameter model, and then we
from
can simulate
measurement.
our own PCB in this software.
Well, so there's some limitations to what this can do. It does not take layout information and like an ODB++ file and bring it in and generate S parameters. That is there. I don't know of any free open source tools that do that, but we can take different transmission line geometries, topologies, and simulate what
Oh,
are the waveforms that we expect to see.
So basically, we can
Um,
very simply specify dimensions of our track on our PCB, length, width, and then maybe PCB stack up. We can put it directly into this simulation software.
well, so this does not do the field solver.
Ah,
So
okay.
so so this but
Oh,
you know what? There's a free tool. So when you look at a transmission line, when we characterize a transmission line, we describe it in terms of two parameters, basically. We describe it in terms of the characteristic impedance and the time delay. And that's the starting place for the simplest model for a transmission line, those two terms. It's
hmm
lossless, but it allows us to calculate and simulate all the reflections associated with that structure.
hmm
And so as a starting place, it's a great model. And that's what Qucs will allow us to do.
hmm
Um, there, there's another free tool that is from Sierra Circuits on their website that will allow you to do just what you said. You
hmm
type in the trace width, the thickness, the dielectric constant, all those features of the stack up of the transmission line, and it will calculate for you based on a 2D field solver. It will calculate the characteristic impedance and the time delay. And
hmm
that information is what you put into Qucs when you build your circuit topology.
hmm
And so Quix is really a simple to use tool to help you kind of learn and explore the behavior of transmission lines. It's I call simulation tools are virtual prototypes. We can build a virtual prototype to explore what happens if we make the length longer, what happens if we change the rise time of the signal, or we change the driver impedance, or change the termination or the routing topology. What's going to be the impact on the signals? And so it's a, kind of, sometimes it's called a digital sandbox or a digital twin of the real world. But I think having a simulation tool available to you is critical for every engineer. And so that's why I like Quix, is because it's free, it's relatively easy to use, it produces results that reflect the real world really well, and it's like accountant, their main tool is a calculator. Well, for a signal integrity engineer, their main tool is going to be a simulation tool. And
hmm
this is, if you don't have any others available, this is a great starting one to use.
Okay, very quickly before we uh, go here. So, can you explain what is difference between the 2D field simulator and this one? So what we
Right.
don't get.
Right. So in the world of simulation tools, there are a couple different categories. There is one that is a circuit simulator. In other words, if you can draw the circuit elements as ideal circuit elements, R's, LC's, transmission lines, if you can draw the circuit elements, then that circuit simulator will calculate all the voltages and currents in time or frequency domain. So those are circuit simulators. Then there are field solvers that take geometry information and turn them into ideal circuit elements, or turn them into behavioral models. And a behavioral model is literally the S parameters. And so two classes, and there are some tools that will do both. They will take the geometry, you give it the ODB++ information, the stack up, the layout, you add connections, terminals to the ends of the interconnects, And it will do all of that. It'll get you the S parameters, and then it will take those S parameters and put them into a circuit simulator and let you use the behavioral model of the interconnect in the circuit simulation.
So basically,
Those,
difference is the
sorry,
input.
it's the input and what level of sophistication in the ideal models it will handle.
Mm-hmm.
For the transmission lines in Quicks, they're only lossless. So that means they have characteristic impedance and time delay. They're high-end tools like Keysight ADS or like Siemens Hyperlinks or Cadence has SI Wave. Um, these are high-level tools, much more sophisticated, that will take the layout information, turn them into S parameter behavioral models, and then incorporate the circuit simulation. So you can now predict, here's what the waveform looks like. You send a driver in on one end, here's what the signals look like at all the other terminals
Mm-hmm.
as well. Those are, we sometimes call those system level simulators.
Mm-hmm. So they include
Incredibly
also
powerful.
the environment and everything.
Yeah,
Mm-hmm.
they're incredibly powerful, incredibly valuable because those literally are digital twins. You take your design as a virtual prototype, you put it in this tool, and it outputs. This is what you would see if you connected a scope to the traces.
Mm-hmm.
Um, and and that's why they cost a lot. You know, one seat for these tools is 50,000 to 100,000 US dollars.
Mm-hmm.
So they're much more expensive, much more powerful. But if they can save you one board spin, a lot of board spins sometimes are in the $50,000 range. And if they can save you one board spin by doing it as a virtual prototype, they pay for themselves in one design.
Mm-hmm.
So those are very sophisticated, very valuable tools and critical for all high-end systems use these tools. And they describe transmission lines not only as lossless, but as ideal lossy transmission lines as well, because, you know, above a gigahertz or so, it's the lossy behaviors of the transmission lines that are so important.
Mm-hmm. Okay,
So those are the high-end tools.
so now I have a question. So
Yeah.
uh, people who are watching may be asking like, okay, but then why should I learn this one if these others are better? Is this going to be like accurate, or are these results going to really help me?
Right. So I think it is really so generally, you know, every tool is different. You know, they all have their nuances, what buttons, where the menus are, but they all work kind of the same way. And if you understand, it's like driving a car. You know, where the start button is on a car is a little different. Some are manual, some are automatic. But if you know how to drive one car, you can learn to drive another car pretty quickly. And the same thing with simulation tools. If you know how to drive one tool, then the learning curve for driving another tool is much less.
Mm-hmm.
And and that's why I think it is so important. Every engineer needs to be familiar with at least one simulation tool. It can be something that is available, that is on their desktop, that is quick and easy to use, they're familiar with. They can answer what if questions very, very quickly.
Mm-hmm.
And so I think it is my professional recommendation when I tell my students and professional engineers, you need to have one tool you're comfortable with. And if in your company you have access to Keysight ADS, for example, that's fantastic. It's a great tool. Learn to use it. If you have a mentor, or is it Siemens hyperlinks, learn to use that tool because the more comfortable you are with it, the lower the barrier to use it, the quicker you can get your what if questions answered with those tools. And if you don't have access, but they're expensive. You know, one seat of Keysight ADS is like $50,000, and for mentors, similar kind of price. And so if you don't have access to those tools in your company, here is this free alternative to get you started.
Mm-hmm.
It's not going to do all the cool things that these $50,000 tools do, but it's not a very steep learning curve. The time invested in learning to use it, I think, is very worthwhile the return that you get from the kind of problems that you can do.
Okay.
You know, there's a term that we use these days a lot, and I talk to a lot of engineers out there and my students as well, and the term is lifelong learner. that all of us, that's your business, is to provide that training education to lifelong learners. And if you're not continuing to learn as a professional engineer, if you're not continuing to learn, your knowledge base goes obsolete in like 3 or 4 years. And so we're all lifelong learners. And my group at University of Colorado in Boulder, we have decided to focus our research efforts on exploring and identifying and exposing tools, low-cost tools that are valuable for lifelong learners.
Hmm.
And that means they're free or low cost. Now, having said that, some tools that are free are not even worth the fact that they're free. They cost too much time in learning how to use them, or they don't work well, or they have bugs, or they don't apply to the kind of problems you care about. So just because it's free doesn't mean it's valuable. And so what we're trying to do in my group at CU is evaluate those tools that are free or low cost that are also valuable.
Hmm.
And that's why I think Quix is one of those tools.
Okay, let's have a
Um,
look on the website.
yeah.
So
Okay.
where people can download it.
So it's really, really simple. So I'm going to open up a browser here, and literally you type in Quix in the browser window, and the first one that comes up is Quix project, and that's it. And then you can open up the website, you can read about it's open source, so it's been around for a long time. So Quix was written by a couple of graduate students, I think it's like maybe 15, 20 years ago. That let's see, here it is. The first release was 12, 11 years ago.
Hmm.
And um, they were using ADS in their graduate work. They loved ADS, but as soon as they graduated, they didn't have access to it
Hmm.
anymore. And so they just said, I'm going to write, or they're going to write their own program that does similar to what ADS does for RF design. And so I refer to this as kind of ADS Lite because it looks kind of like ADS, doesn't do nearly the stuff ADS does, but it's a start, and it's free.
Hmm.
And so you can read a little bit of the history here and what it is and all this stuff. And then if you want to download the executable, depending on the operating system, so it runs on every operating system. If you click on the Windows operating system, here's the GitHub or SourceForge they use. And the latest one is the 0.19. And uh, let's see. So look at that. They had 12,000 downloads last week. So you click on that one, and now you decide here which tool you want to download it for, the Mac or Windows, and then you can download the zip file, and then it's just a executable.
Hmm.
And then so there's some nuances in using it. So it's not 100% intuitive, but we're going to do some more videos on Quix, and we'll get them on your website that will walk you through start to finish. How do you get started with Quix? Um, and I'll also mention that, when it comes to free Spice simulators, probably the most popular one is LT Spice. It's been around for a long time, started by Mike Engelstrom or Engelhart when he was at Linear Tech. That's why it's LT is Linear Tech Spice. Analog Devices bought Linear Tech, and they've been hosting LT Spice. Mike actually spun off when Analog Devices bought LT Spice or Linear Tech. He spun off and worked for Cuervo, and he created a brand new version of Spice called Q Spice that's available from Cuervo. They're both completely free. LT Spice is a little old, it's dated. Um, it's really easy to use. It's got a lot of capability to it. So that's another free tool that's available. QSpice is another free tool that's available. And I teach sophomore circuits, or have taught that in the past. And the Spice tool that I use for my circuits class is Symmetrics. And Symmetrics has a free version called Elements. That is another Spice simulator. So there are a lot of Spice simulators out there that are free. I like Quix because it also understands S parameters,
Hmm.
and none of the other tools really do that.
Hmm.
So that's why I'm going to show you Quix. The simulations I'm going to show you, you can do with any Spice simulator. There's nothing special about it. They're kind of cool. You can play around in this virtual space, and you can do more in Quicks than you can for signal integrity applications than you can do with some of these other spice simulators.
Okay, let's
Okay,
build something.
let's build something.
Yeah,
So
because
so
you are
here's
very busy. I
yeah.
know maybe some people will be like, "Oh, you keep interrupting Eric," and I'm like, "But
No, that's okay. It's
always
just
today we only have
you.
like 45 minutes."
Yeah, that's okay because we're going to have a lot more details available online. And so this is the teaser to give folks a sense of what it can do
How to
and a little
start
bit of
with
how
it?
to do it.
Yeah,
Huh?
how to start
Yeah.
with this?
Yeah, how to start. So we're gonna I'm gonna create a new project here. I think I actually have a project set. Oh yeah, I have a little blank page. This is starting with a blank page,
Mm-hmm.
and we're gonna build a really simple simulation. The most simplest one is we're gonna do the step response of an LRC circuit or RLC circuit, and we'll see some ringing there. So here's our schematic page. It's blank, and so we're gonna add some components. So let's build an RLC circuit. So here's the R. Let's see, here's the L, and let's grab a C. Here's a C. And personally, aesthetics, I like to rotate my C's so they're vertical. So I'm going to come up here, and there it is, rotated. And now we're going to connect them together. And so here is our circuit. And we need to have every splicer needs a circuit ground. And now I want to drive it. So we can, if we I'll get rid of that one there. If we want to change a value, so let's see. So if I have an RLC circuit, you know, it has. I'm going to look at the voltage across the capacitor
Mm-hmm.
here, and an RLC circuit has uh, a couple of features. One is its characteristic impedance. That's the square root of L over C. And it also has the ringing frequency, resonant frequency, and it has a damping term, the Q associated with it. And that's all about these values. And so the characteristic impedance is the square root of L over C. So I'm going to make these so that they have the same value in units. So the characteristic impedance is 1 ohm. And so I'm going to make that capacitor there 1 nanofarad. Now the square root of L over C is 1, so it's a 1 ohm characteristic impedance. And that means the damping, if I want to have it underdamped, I want the resistance to be less than twice the characteristic impedance, so less than 2 ohms. So I'm going to make this, I'm going to make it, let's see, we'll make it really underdamped. We'll make it 0.1 ohm. So now I know what to expect. I'm going to see this guy ringing, and the ringing frequency is 150 megahertz divided by the square root of LC. This is square root of LC is going to be in nanohenries and nanofarads is 1, so it'll be about 160 megahertz is the ringing frequency. Now to drive it, I'm going to create a step signal, step
Mm-hmm.
response, really common signal. And so we're going to come over here, we're going to select some other components or sources, and we're going to grab a pulse. Let's see, where's my voltage? Here's current pulse. Here it is, voltage pulse. And so you can see, it's very typical of spice simulators. You have all these different kind of sources you can generate. And that's why if you learn Quicks, you can use any version of Spice.
Mm-hmm.
The location of items is a little different, that's all. So here's my voltage source, and now we're going to make it a step signal. So here's the start voltage 0. Here's the final volt. It's going to turn on 0 to something, turn on to 1 volt. Here is the on time. This is how long it's going to stay on before it turns off.
Mm-hmm.
Here's the rise time and the fall time.
Mm-hmm.
And and because we know it's going to ring at 150 or 160 megahertz, I'm going to use a nanosecond rise time is short enough. It will see it. It will drive the ringing.
Mm-hmm.
We'll change this rise time. We'll see, oh, too long a rise time, and we don't have frequency components down up to 150, 160 megahertz. We don't see the oscillation. So we use 1 nanosecond. Um, and and of course we have to add the ground reference to it. And of course, for an ideal voltage source, its output impedance is 0. And so that's okay because we have a resistor over
Mm-hmm.
here. So let's connect it in. So here is our circuit. And so it takes, well, maybe 30 seconds to build the circuit if I didn't gab all the time about it. And we're going to simulate this in the time domain, and we're going to look at the voltage from the source, that's the step, and we're going to look at the response across the capacitor. So we're going to add a couple of probes here. So here's the first probe, and this is going to be, I'm going to call this V of the source, and we're going to grab this one over here, and I'm going to just call this V of the capacitor. I'll just call it VC, V of the capacitor. Now, so we've told it what we're going to measure. Now we need to simulate it. And so we add, and this is where it's very ADS-like. ADS, you grab a simulation engine and you place it on the circuit page. So we're going to grab a simulation engine and we're going to do a transient. So here are all the simulations we can do. We DC, it's kind of boring. The transient, that's the time domain simulation. This is sweeping AC. We do S parameter simulation. That's what I love about this. And we can sweep parameters as well. So, oops, I want to do transient simulation. So we'll grab this guy here. And here's where, whenever you set up a transient simulation, you always have to think about, okay, what do you expect to see? This is rule number 9. What do you expect to see? And so this is going to be, it's going to ring in 160 megahertz. And so if we go for, that means what is like 6 nanoseconds as the period. So, if we go for, 50 nanoseconds, maybe 100 nanoseconds, we'll see all the ringing should be gone roughly. So let's go to 100 nanoseconds. So I'm going to stop at 100 nanoseconds. And now, as a rule of thumb, we want to simulate at least 1,000 points. These simulators are so fast, 1,000 points is in a blink of an eye. So we're going to use 1,000 points here, or I shall make it 1,001. They'll have nice even numbers. And that means that if it's for a total of 100 nanoseconds, we're going to simulate every 100 picoseconds. Okay, and so general rule of thumb, I always like to save just because you never know. And so I'm going to save it here with just change the name, and now we've got it captured. And now we're going to simulate. And there's one other thing I'm going to do. So when we simulate, we're going to get results, and I want to put the plot on the same page. So I don't want to open up another window for it. And so I'm going to make one small change here, and under the document setting, I don't want to open up a data display another window after simulation. I don't want to move the window. So I'm just going to make that change. I don't know why that's the default, but it is. So now I'm going to simulate, and I'm done. So if you blinked, you missed it because it's so fast. But okay, so I've got the measurements embedded here in the tool. I want to display them. So I'm going to come over here to my diagrams. I'm going to grab a Cartesian plot. I'm just going to put it over to this side, and we're going to plot the voltage of the source and the voltage on the capacitor. So I'm going to do this one. I'm going to do this one, and here it is. So we're looking at, oops, let me zoom into this guy. So here is, on the vertical scale, is the voltage. This is all auto scaled, but that's okay. This is time. Here's our micros, or 100 nanoseconds time delay. The red is the red is the voltage coming here from the source. That's our step edge. Turn it on. And then here is the oscillation. And let's see. So the Q is the characteristic impedance divided by the resistance. So let's see. What's the Q here? It's the impedance is 1 ohm, and this is, the R is 0.1. So the Q is the impedance over R. That's 10. So rough rule of thumb, the Q is a kind of a measure of how many cycles I see before I get to the 99% level. So let's see, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And there we go. So that's a measure of the Q. And let's see, so I expected about 6 nanoseconds as the period. Here is 20 nanoseconds here. So I have 1, 2, 3, a little bit more than 3 periods in a 20 nanosecond. There's our 6, roughly 6 or 7 nanoseconds per period. So it's exactly what we expected to see. And we can make a little change. So suppose that we made the R larger. What do you think is going to happen to the damping?
We will see less.
Yeah, it's going to die off more quickly.
Yeah.
The Q will make R bigger. The Q will get smaller. The number of cycles before it damps is going to reduce. So let's go in here and we'll make this make it 0.5 ohms. So 5 times higher resistance, 5 times less number of rings. So here we simulate it, we're done, and there it is, exactly what we'd expect. And if we want it critically, so we had it underdamped, so it was ringing a lot. If we made the Q equal to a half, no, I always get confused, is it a half or 2? Let's see, I want the Q to be 2. No, I'm sorry, I want it to be a half. That means critically damped. And so the impedance is 1 ohm, so I want the Q equal to 1/2, so I want 1 ohm over R to be a half, I want R to be 2. So let's make this 2 ohms, and now it should be critically damped. And there it is. Now, if I made it, now all the information I care about is happening right here. And I've got all this time here. I don't care about all this time. I care about what happens here. So I'm going to come over here and I'm going to change the time to be 20 nanoseconds. And we still have our 1,000 points. Let's just re-simulate it so we can see that. So here's our critically damped. If I make the resistance smaller than this, I'm going to see a little bit of ringing. So
I'm going to interrupt you.
Yeah, yeah.
Could we add frequency domain pictures? Because I would like to show people what we will see there.
When you say frequency, what do you mean? The spectrum? Or do you mean sweep frequency and look at a
Or
Bodie
impedance,
plot?
or we can put the impedance.
Oh, you want to see the input
Yeah,
impedance?
yeah.
Ah, okay, sure. So here's how we do that. So this is a feature in every version of Spice. We can build an impedance analyzer really easily. And the way we do that is we use a constant AC current source, because the definition of impedance is equal to V over I. And if I is, that's what we're going to control. We're going to use a constant current source, AC constant current source. We're going to control I. We're going to make I equal to 1 amp amplitude. That means that the impedance of when we simulate our circuit, the impedance is literally the volt. We can only simulate voltage and current. That's it. Those are the players. And if we use a constant AC current source, then the voltage is exactly, or I'm sorry, the impedance is exactly equal to the voltage. So let's do that. So we're going to take the same circuit here, and I'm going to grab a source. Let's go to our sources, and we're going to use AC current source. So let's see, here's AC voltage, here's AC current. And so I'm going to rebuild this circuit, and here is, so I'm going to turn it on. I want 1 amp. So I'm going to make this amp here. And the frequency, we're going to change that by simulation. We're going to sweep whatever frequency we want. Okay, and let's see. So the other thing we need to do is we need to ground this guy. So this circuit here is going to generate an AC current with a 1 amp amplitude and use whatever voltage it needs to in order to do that.
Okay.
One important problem that we have to watch out for, and I just wrote an article, so all your readers need to go to signalintegrityjournal.com. I'm the technical editor there, and I just wrote an article that came out last week about how not to blow up the universe. And if we just simulated this AC current source open at the end, we would blow up the universe. Because in order to get 1 amp, and this is open, that takes an infinite voltage, and that blows up the universe. So you have to have a DC path to ground for any current source so that we don't blow up the universe. So I'm going to add a whopping big resistor over here just so that we keep the universe from blowing up. So I'm going to add this here, and I like, aesthetically, I'm going to rotate this around, and this resistor, I want it to be really big. I want it to be 1 e to the 9.
So it doesn't really influence our
right. It's way above anything, but I don't want it to I don't want a constant current source of any sort with the potential being an open, otherwise the universe blows up. So now the voltage here is literally going to be the impedance of this guy times 1 amp. That is the voltage. And if this is 1, the voltage here in volts is equal to the impedance here in ohms. Now let's build it. Let's just take our circuit right here. So we'll take this guy here.
And can we use also parameters, like, so we don't, we can...
What a great idea. So let's do that. So here's how we grab parameters. So I'm going to create a an equation here. And now let's do the R over here. So we'll do R1, a very clever name. This is going to be in ohms, and we'll use 1 ohm here. So I'm going to add that in. Let's put a C in there, a C, 1. And so the units have to be in farads or henries or ohms, SI units. So this is going to, I always like to put the units to remind myself,
Mm-hmm.
oh, this is what it is.
Mm-hmm.
And so this will be 1 e to the minus 9. That's the
Mm-hmm.
nanofarad. We'll add that in. Oops. Oh, that was really stupid. I have to, it's a little picky about the values and how we do this. So I have to add this in. And then let's do the L. So do L1 in units of henries. And let's see, L is going to be, oh, nanohenry, 1 e to the minus 9. I'm
Mm-hmm.
going to add that in.
Mm-hmm.
And so here are our parameters. So
Okay.
let's go back in here, and I'm going to change this R to be R1,
Mm-hmm.
and there we go. There's R1. I'm going to change L here to be L1 in henries, and there it is. And I've got the value here, and I'm going to change this, and this is going to be our C1 in farads.
Mm-hmm.
Okay, and if you don't have units here, that means there's the SI units. Oh, you know what?
You
And
can, yeah.
I don't need that. I can just grab this guy now that he's all created. So I'll grab him, and now I change the parameter values once over here, and that's going to ripple into both of these. So look at
Yeah.
time and frequency. Now we're going to connect them up, and now the voltage here that I measure in volts is literally the impedance looking
Mm-hmm.
in here in ohms.
Mm-hmm.
So let's grab our label here, and I'm going to call this impedance of circuit 1. Now, I'm simulating this. I'm going to zoom out so we get a little bit more room here. I am simulating this guy here in in the time domain. I want to simulate this guy here in the frequency domain. So I need a frequency simulator, and this is called AC simulation. So we're going to do simulation. Here's AC simulation. Now, do that over here. I'm just gonna move these guys over a little bit so there's a little bit more room. Here we go. So here's my transient simulation for that one. Here's my AC simulation. And let's see what frequency. So whenever I look at impedance, this is a diversion, I always want to look at impedance versus frequency on a log-log scale. Do you know why that is?
Because it's nicer.
Well, because on a log-log scale,
They are
the impedance, exactly. The impedance
lines.
of a capacitor is going to be 1 over F. It's going to be a straight line. The
Yeah.
impedance of an inductor is a straight line going up. And so at a glance, I can tell what the impedance is like looking at a log-log. So I'm going to sweep the frequency, but I'm going to sweep it on a log scale.
Mm-hmm.
And now what's frequency range? Well, we already said that, the resonant frequency was um, we said 160 megahertz. So, maybe I'll go from, 1 megahertz to a 10 gig. That's plenty high. So that's 4 orders of magnitude. I'll do 100 points per decade. Um, and there we go. And so now we're going to do 2 simulations. We're going to do a transient simulation, look at the response here, and we'll do a AC simulation. Now, let's go back to what we had so we have something that looks cool. So we're going to do our underdamped case.
Mm-hmm.
And so that's going to ripple, and that's going to make that one and that one. Okay, so now this is going to be the transient response. This is going to be the AC. So let's save that just so we don't crash. And we're going to simulate. Ka-chunk, ka-chunk, ka-chunk. It's taking a little longer. Oh, you know what? We should probably increase the time here a little bit more so we can spell the ringing.
Okay.
But there's the ringing, and now so we'll do that for the next time. We'll have it ready to go. And now let's add the plot of the impedance. So we're going to come over here to diagrams. We're going to grab our plot over here, and we want to plot. Let's see. Here's the AC simulation. Here's the impedance. Z1 is the impedance. So there it is. And I think that's the one that I want to use because it's going to sweep it with frequency. We say okay, and um, and now here's what the impedance looks like. I'm going to zoom in so you can see that a little bit better. Now here's the I wouldn't say problem, but here's the limitation is the default plotting is linear. I like plotting log log. So we're going to come over here and we're going to come over here to the properties for this plot, and we're going to plot the log of the x-axis and the log this, and we're plotting the impedance on
Oh, so you
the
not
left
only
axis.
need to set the simulation logarithmic, but also the graph has to be logarithmic.
Right. And we can do
Oh.
the graph any way we want. It's just
Mm-hmm.
that we're just graphing the vectors that were calculated. And
Oh.
here we are. And is that cool or what? And so now we're looking at the transient. Let's do the
Yeah, rerunning.
longer
Yeah, yeah,
time
yeah.
for the transient simulation here. So here's that transient simulation. Here it is in the frequency domain. And sure enough, hey, it's an RLC, it's a series circuit. And so here is the impedance at the low frequency end is related to the ESR, and that was zero point 0.1 ohm, and there it is,
Mm-hmm.
0 0.1 ohm.
Mm-hmm.
We see the behavior over here for an ideal capacitor of 1 nanofarad. Here's the behavior of ideal inductor here from this guy. So it's a series RLC. Now this is underdamped, and we have really sharp
Mm-hmm.
peak. And this is a high Q. And after all, we saw it was 10. Let's go back and make this critically damped. Do you remember what that resistance was for critically damped?
Uh, the other one was 0.5. No, not the.
Well,
It's
that
a
was
small.
underdamped, so it was two ohms. So let's
Oh,
make
two.
it
Ah,
2
okay.
ohms. And what do we expect to see? We're going to see that critically
Nice.
damped signal, and we're
Yeah.
going to see this. Its low point here is going to be 2 ohms. It's going to be down to here, and it's going to be kind of a little smooth
Mm-hmm.
little plot. So let's see that. And there we go. Critically damped, and we see here it is, down to 2 ohms for the ESR. So that's what we can do with Quicks. And in full disclosure, any SPICE simulator tool will do this. It's just that I find the graphical output for Quicks and the ability to grab circuits and put them there and do different simulations, I just found it so much easier in Quicks than the other tools.
Mm-hmm.
That's why I'm a proponent of it.
Can we put that
Okay,
also 0.5? I just would like to show
sure.
like the peak is not going to be so sharp, but it
Yeah.
still will be there.
So this
Obviously.
is the value of, parameterizing and doing the what ifs that you can answer those questions. Now, I always say, can you see my hat as rule number
Yes.
9 there? I always say, if you're going to do a simulation, you know that expression, garbage in, garbage out? It's very common in the States. And it was invented for simulation because it's easy when you push that run button, you're going to get a result. Unless you're blowing up the universe and then it'll barf on you. But if you're not blowing up the universe, you're going to get a result. The challenge is the result meaningful? Is it appropriate for what you're trying to do? And that's where one of the most important consistency tests before you push that run button is anticipate what you expect to see. And that helps. I said at the beginning, this is for lifelong learners. We want to use this tool to help us accelerate up the learning curve. And that's where thinking about ahead of time what you expect exercises your understanding. And if you're correct and you see what you expect, you get a nice warm feeling, it builds your confidence. And if you're not, if it's different, then you look to see, did I screw up the simulation or is my understanding off a little bit? And so we're going to make the resistance point half an ohm. So this should drop down back to half an ohm. And we're going to see a little bit of overshoot here. Let's see if that's what we get. So we run the simulation. Now, okay, it's a couple blinks of the eye. And that's not what I expected to see.
Oh,
Oh,
it's still two. It's still two.
yeah, very good. This is why rule number 9 is so important because it's not what I expected to see. And I tell my students that most of the time when it's not what you expect to see, for me, because I screwed something up. And here it is. I typed in 0.05, but I didn't push enter.
Mm-hmm.
I didn't lock it in. So I do 0.5 and now we lock it in. Now we got the new value. So now let's try it. I wish I could say I did that on purpose to show you how important rule number 9 is, but sometimes as I get older, I'm doing it less on purpose. So, so here is that ringing behavior because it's underdamped, and here's a little sharper peak here.
Mhm. Now,
So
I would like to point out because this is very interesting, and I think many people they may not know why this impedance graph is so important because it is telling us how dangerous these may behave for some frequencies, and if these frequencies are actually in the circuit what they are running, then they can have like problems. That's why it is important.
yeah, and we with an RLC circuit, it is simple enough that we can analytically, with paper and pencil, calculate some of its important features. And I think it's really important to do that. And in addition, sometimes other than just estimating the Q and the number of cycles, it's hard to know how significant the ringing is going to be. And that's where doing the simulation is really powerful.
And now we
Um,
would like to go more practical. So we did this circuit, uh, and how this can be applied for PCB layout is PCB tracks are inductance and capacitance. So let's do
e-
some kind of PCB
Except
track.
I'll do one caveat to that. That thinking about a PCB trace as an inductor and a capacitor is an approximation, a low frequency approximation. In reality, the um, the interconnect behaves like a transmission line. And there's a connection that is, if I know the impedance and time delay, I can tell you what the L and the C values are. In fact, we're going to do that. But it's the LC thinking is an approximation. Whereas the transmission line, it's an approximation, but it's a much higher bandwidth approximation.
Okay, so let's explain what's the difference. What's the difference? So transmission line, it means it's many capacitors and inductors in series or in row or something.
Kind of.
Okay.
I like to because I always say that, if you if you think about a transmission line as an approximation of a bunch of LCs, it screws up your intuition. Because if you have a bunch of LCs, like here's one of those elements. So I'm gonna just build that over here. So
Oh, I know.
so here's that approximation. So if we were to take this guy here and make here and here and here and here and connect them all together, and you think, oh, that's a transmission line, LC, 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 LC. This is an L is kind of like a speed bump, right? It slows down the edge. A capacitor is like a pothole. It holds the charge there. And so if you're thinking about a signal traveling through this interconnect, there's a speed bump, a pothole, speed bump, pothole, speed bump. It's a bumpy ride. That is not how signals propagate on transmission lines. So this is an approximation that is not a very good approximation.
Okay.
And so I always say, instead of thinking about a transmission line as a bunch of LC, 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 what you really want to do is learn how to think about I'm gonna block those out. A better way of thinking about a transmission line or an interconnect on a board is a transmission line. And so that is a completely different circuit element. So we're going to come over here to transmission lines. So Quix was designed for RF applications. And so there are a lot of transmission line elements to pick. For signal integrity rather than RF, the approximation we want is this guy here, uniform transmission line. So all of these things here is LC, 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 LC. Much better approximation for the behavior of a real interconnect is this guy here. It
Hmm.
has a characteristic impedance. And so the way Quix defines a time delay, so it has a characteristic of a time delay. The way Quix defines a time delay is the physical length
Hmm.
of an interconnect with air as the dielectric.
Hmm.
And so for 1 nanosecond, speed of light is, I can go 300 millimeters per nanosecond. It's 30 centimeters per nanosecond. That's the speed of light. So if I wanted a nanosecond long, I would make the length 300 millimeters. Or if I do it in meters, it's 0.3 meters. So now this is a transmission line with a characteristic impedance of 50 ohms and a time delay of 1 nanosecond. And this is a much better approximation for the behavior of a real transmission line than these guys. And I have a textbook out. It's called something about characterizing transmission lines and TDR or something like that. And I go through a lot of details showing the difference between this approximation and adding a whole bunch of sections. It gets better and better, but it's still a crappy approximation compared to a real transmission line. And we're going to take this guy here and this, and we're going to do exactly these
Okay,
same
I'm clear.
simulations, and we're going to compare them. So here's how we're going to do that. So I'm going to take let's do the impedance first. So here's my impedance analyzer. So I'm going to build that source over here. And the label for this is the impedance of the transmission line. Let's see, so here we go. I want the impedance of the transmission line, or T element, we sometimes call it. And I want to connect these guys up here, but I'm going to connect this in directly. So let's see, I need a wire here and here. The other end of the transmission line, I'm going to keep it open. Now, Spice doesn't like having open terminations.
So
Doesn't know
very
what to
high
do with that.
resistor.
Yeah, I'm going to add a big resistor. So I'm just going to grab a resistor here. Well, I'm going to grab a new resistor. Let's go to lump circuits, grab the resistor. I'm going to place it over here. I'm going to make this 1e to the 9. Doesn't really matter. And then I'm going to put a ground on one end of it over here and connect these guys up. And
so
there's
this
my
is like
circuit.
input of a buffer, for example, or something.
Yeah, this is so we're looking at impedance. So this is a special circuit. We'll go back to the transient one in a minute here, but this is just looking at the input
Okay, just to
impedance of a
see.
transmission line.
Just to see
Now
the graph.
here's where we're gonna do something clever here. We're going to create a parameter here, and this parameter is going to be the impedance of the line. So Z0 of 1, and I'm going to make that, we'll call it 50 ohms, but we'll change it to anything we want. We're going to apply that, and I'm going to put the time delay here as well. The time delay of 1 in units of nanoseconds, and we'll make it 1 nanosecond. And so I'm going to add that as my parameters here. But for Quicks, it doesn't understand a time delay, it understands a length. So I need to add one more parameter here, which is the length of the line in meters. I have to remind myself, well, that's in meters, and that is going to be 0.3 meters per nanosecond times the time delay in nanoseconds. So this is the advantage of parameterizing.
So
right?
you can do calculations behind.
Yep. And in Quicks is smart enough to look at your equations and decide what should be calculated before we do the simulation and setting up, and what should be calculated after the simulation. So we can also do calculations on waveforms as well. So, and now here's the cool thing I'm going to do. I'm going to make the RLC, I'm going to make that equivalent to the characteristic, the transmission line, because this transmission line, it's a 50 ohm line, and it is 1 nanosecond long, and we can approximate that with a capacitor and inductor. And how much capacitance is there? So here's where, knowing a little bit about the behavior of transmission lines is valuable. The amount of capacitance in a transmission line is literally the time delay divided by the impedance. And so I'm going to come over here, and you know what I should have done, and I'm going to do that now. For characteristic impedance, I like Z0, so I'm just going to readjust the name of that. And now I'm going to put those parameters in here. This is Z0, Z0 for value 1. And let's see, the length here is going to be the length of 1 in meters, and I'm going to put that in there. So now, with no units appearing here, we're using the SI unit, so it's meters. So it's the same transmission line that I had before. But now I'm going to come over here. I'm going to put in the value of the capacitance I think is in here, and I'm going to make this capacitor. This capacitance is really the time delay in nanoseconds. I'm sorry. It's the time delay I have capacitance in farads, so I need the time delay in seconds. So I need to take that and multiply it by 1 e to the minus 9. And it's the time delay in seconds divided by the characteristic impedance, Z naught of 1.
Yeah, but one maybe is not one missing the TD underscore one.
Oh, very good. See, I'm glad you're paying attention here. So I need to underscore 1, and we apply that. There it is. And so um, Qucs is smart enough to look at, I got a variable here. Where's that defined? And look through all the equations. Here's where it's defined. So that's the impedance. The L is the time delay times the characteristic impedance. And so L is the time delay of 1 in nanoseconds times 1 e to the minus 9. That's how many seconds times the characteristic impedance that we have defined. Okay, and then the R, well, there's no R here, right? So I'm going to make R really small. I'm going to make it a milliohm, 0.001. And we know exactly what it's going to do. We saw this before. Whatever that capacitance is, and so we can do this in our head, right? It's 50 ohms, and so it's 50 ohms divided, I'm sorry, here we are. It's 1 nanosecond divided by 50 ohms, so that's 20 picoseconds. So that means, I'm sorry, it's 20 picofarads. So this is going to be 20 picofarads, so the impedance is going to go way up. And the inductance is, let's see, 1 nanosecond times 50 ohms. This is 50 nanohenries. So I can tell you exactly what the inductance is going to be. So it's bigger than this, so the impedance is going to go down. So it's going to shift a little bit, right? And I put the resistance really small, so this is going to go way down. Now this guy doesn't have a value of the of R, and so I don't know, it'll drop down as well. So here's my circuit. Let's save this, and now we'll simulate. And it's taking a little time. Chunk. There it is. Oh, okay, I made the Q really high, so it's got a lot of ringing. It's ringing forever. Here is that impedance profile. It's going down here to the, I didn't happen to hit the lowest impedance, so it only went down to 0.3 ohms here. And now let's add this impedance over here. This is the impedance of the circuit 1, the RLC. Let's add the impedance of this guy. So I'm going to come over here. I'm going to say, let's go find that impedance of the transmission line. That's this guy here versus frequency. We'll add him in, and there he is. Ooh, look at that.
So
Now I'm
why
going to
it's
zoom in
not
so we can
same?
see it. Oh, yeah. First off, look at the low frequency, right? I nailed it. Look at that. They're exactly the same, right? Because I know in a uniform transmission line, the equivalent capacitance is the time delay divided by the impedance. Darned if I didn't get exactly that value. But now you're saying, well, wait a minute. Yeah, you got the capacitance, but you're off over here. What did we say about this model compared to this model? This is an approximation. And it's not that great of an approximation. And so it's great at approximating the behavior over here of the capacitance at low frequency. It kind of sort of gives us a dip over here. Yeah, we kind of see the dip, but we miss the resonant frequency of this is different from the resonant frequency of this. And oh my gosh, this model here said the impedance just keeps going up. But this model says, uh-oh, that impedance oscillates between high and low, open and short, open and short, open and short. And so this is only an approximation. So that's what you have to watch. That's why, okay, at low frequency, low frequency means when it's electrically short, it's going to look like a capacitor if the end is open, or look like an inductor if the end is short, which is fine. But when it's electrically long, it doesn't look like LC anymore. It looks like a transmission line, a completely new beast that has a completely different set of properties that are really important. And using simulation, we can explore some of those properties. So this is the frequency domain, and looking at the we call this the input impedance of the transmission line in the frequency domain, or the input impedance of the RLC circuit in the frequency domain. Very different from the instantaneous impedance I see when I walk along this transmission line. They both have the word impedance in them, but they're two completely different impedances that we're looking at. So we're running out of time here. I think this was really useful to kind of show the value of how much you can learn using a simulation tool and how easy it is to use a tool like Qucs.
Yeah.
And so far, nothing here really required Qucs. You could do this on LT Spice, you can do this on Symmetrics, but you can say it's really quick and easy doing it on in Qucs. And another time, and on your website, we'll put some videos of doing transmission line circuits, and we'll look in the time domain at looking at launching signals in and reflections in those transmission lines.
I would like to just add, so anyone who would like to kind of simulate the tracks, then just use the transmission lines and they can then basically
Yep,
see the behavior
exactly. All you need to
signal.
know is what the impedance of the line is and the time delay, and you can get that from the Sierra Circuits online free 2D field solver tool.
Okay, and I wanted to mention, do you go to DesignCon?
Yes, so I'm going to be at DesignCon. I know you're there. We always enjoy a chance to get together in person at DesignCon. I'm going to be doing got one of my students doing a technical talk, and who I think you have had on your videos. Adinath Penny
Yeah, yeah.
is going to do a presentation. We'll do it together. And then get another technical talk. Gonna do a couple of chiphead theater presentations. Be wandering around the floor. Hope to see all of our friends there at DesignCon. Every year it grows. It's the place to be if you're doing anything with signal integrity, power integrity, EMI, and it's a great opportunity to hear the latest technical talks as well as walk the show floor and talk to companies that are producing tools and products that are use best practices for our industry.
And meet great people.
And meet great people. Just walking in the hallway, you'll see a lot of experts walking around.
Thank you so much, Eric. So next time we will continue. Then we can do the
Yeah, we'll
transmission
do some
lines.
more stuff.
Okay,
Okay,
thank you, Eric.
great talking to you.
Bye bye.
Bye-bye.
And that's everything. Thank you very much for watching this video. By the way, we are preparing some very interesting tutorials, so if you don't want to miss them, hit the subscribe button. If you want, you can also check out our FedEval online courses, where you will find everything important from basic board design up to advanced hardware design and PCB layout. The link is in the description. That's all for this video. Thank you again. Don't forget to leave your comments and see you next time. Bye.